Okay, we are live now. So today we will discuss double integrals over rectangles.
Hmm.
So today we will get the feel of it, like
Hmm.
what is exactly double integrals mean, or what is the significance of it,
Hmm.
what does it represent.
Hmm.
So we are looking at double integrals over
Hmm.
rectangles.
Hmm.
So let us try to feel it. So first, in order to understand double integrals, we have to relook at single integral.
Hmm.
Then we will get a very clear understanding what is happening in the double integral. So we are already aware that the single integral is used to calculate the area under the curve.
Hmm.
So very quickly we will just revise it. The technique we will revise that how single integral is able to calculate the area under the curve, which is a 2D curve.
Hmm.
So let us look at it. So I will be uh, referring a graph. That graph will help us. So let us fetch a graph. Let us bring it over. Let me just grab it. So this graph will help us
Hmm.
to explain what is happening in single integrals. So is the graph visible?
Yes, sir.
Okay, nice. So see, we are already aware that here we have a function, like I will use a highlighter.
Hmm.
So see this y is equal to fx, it's a function. And this is the graph of function, the green line.
Hmm.
This green line, it's the graph of the function. And we have to find the area under the curve. Area under the curve is this region. Area of this region. And this is a 2D region. It's a plane. So the area we have to find. That is the requirement. Now, what is the technique for that? Let us try to understand. The shaded region which I have to find the area of that. So area under the curve. So the technique, if we remember, what we used to do is we used to take a very small region or a part of x. We used to take a very small part of x. Let us suppose we are interested in a region A to B. In the region A to B, we are breaking those, like x belongs to A to B. We are breaking this region into n small part where delta x like the width of each rectangle is delta x, isn't it? Let me draw it again.
Hello, yes, sir. Yeah.
Delta x.
Right.
Now, what is this delta
This is
x?
sir, this is Riemann sum, right? Like this
Yeah,
will lead
yeah,
to, yeah.
yeah, that is right. So let me write it. So basically, we are solving this uh, area under the curve using the Riemann sum. Riemann sum technique. So what we are doing is that the region A to B, we are breaking it into small, small rectangles. So delta x, we are breaking into delta x, wherein every delta x it is b minus a by n. Delta x is b minus a by. So this is the idea. And we are breaking this region A to B into n parts. So delta x we got. Now what we did, like this is the delta x in the graph. Now what we have to do? We have to find the area of this rectangle, single.
Hmm.
So that will be, that we can call it like small area, dA. That we can call it dA. dA means small area. So this small area. So this small area will be, what is the area of the rectangle? Like width into height. So delta x. And what will be the height of this rectangle? Height of the rectangle will be given by the function at that point.
Okay.
F of x. And I have to make this delta x very small. So now it is delta I. Now it is delta I. And when I make this delta x infinitesimally small, like very, it is very close to 0, then I will get dA. So I can write it fx dx. Now this is just for one area, one box or one rectangle. But I want it for all the rectangles. So I will do the sum. Like what I will do, each area I will calculate and I will just sum it up. I will calculate this area, I will sum it up, I will calculate this area. So each individual areas I will calculate, and this is the formula for that, fx dx, wherein dx will be same for all. Fx value, it will depend on the curve. Curve will give me the fx value at that point. This graph will give me the value of fx at that point. And based on that, I will be able to calculate all the rectangles, all the areas of the rectangles one by one using this. And I have to do the summation of it. Like whatever areas I am getting, I just have to keep on adding it. And I is equal to, and how many parts I am breaking it? I am breaking it into n parts. So this is the idea. 1 by n dA. So I can write it like this to be more precise. To be more precise, I can write like this. Total area under the curve is equal to summation of I is equal to 1 to n dA. Or what is dA? fx dx. Now I want to break this, and I want to break this rectangle into infinite parts, because the smaller the width, the smaller the delta x, the more accuracy we will get in terms of finding the area. So I will say that the area under the curve will be limit n tending towards infinity summation of I is equal to 1 to n fx dx. Any doubt till here?
No, sir, no doubts.
Now we know that limit n tending towards infinity I is equal to 1 to n. It means that we got an infinite series. We have broken this region into infinity parts, like infinite numbers of small rectangles. We are calculating the area of each rectangle and summing it up. So we will get an infinite series. And according to the notation, this limit n tending towards infinity 1 to n, it is integration. It is the integral, and it is the integral over the region a to b. So I will write it with a different color. So this I can represent something like this. This will become integration from a to b fx dx. This is the area under the curve. So we saw that single integral is a powerful tool. Single integral is a very powerful tool to calculate the area under the curve, and it works also. Like the logical part is very clear to us, and we are convinced that okay, with single integral we can calculate the area under the curve, and we have been doing it. So this motivates us to think one step forward. Here the function is a one variable. It is a single variable function. What if I have a function with two variables? Because we know that a single variable function will always represent a curve on a plane. But a function with two variables will represent a 3D figure. It will represent a solid object. Why is it so? Because z is equal to f of x comma y. And what it is? It is a function with two variables. So if you draw the graph of it, you will have an x-axis, you will have an y-axis. For every pair of x and y, you will get some z. So some points you will get in the 3D plane. And when you merge those points, so you will get a 3D object. And for 3D object, we are interested in calculating the volume. So we can extend this idea to functions of two variables to get the volume. And that is what we will be discussing. So now we will be focusing on double integral.
Yes, sir.
Double integrals. In double integrals, we are interested in. So let me bring this. Picture over here. Now, as we have already seen, that if we have a function of two variables, as you can see in this graph, we have a function of two variables, y is equal to f of x comma y. So I can plug different values of x and y, and correspondingly I will get z. And if I plot those points, I will get a surface like this. So this is a surface, and it is on a 3D plane. And definitely it will have some height, and hence we can calculate the volume of this solid object. So there is a scope of that. And that is what we will be doing. Okay. Now let us see how we will do. So it is very clear to us. We are convinced that whenever we have a functions with two variables, the graph, if we draw, we will get a solid object. And whenever we are talking about a solid object, we are talking about volume. Now one more representation we can make use of here. Let me keep it both side by side for better understanding. Now I have a problem in my hand like this. Let me arrange it properly so that you can focus on the given scenario properly. Yes. So see here the idea is pretty simple that okay, whatever function that the 3D curve I have, I can convert it into something like this. Like this is the actual graph. This, wherein this is the solid curve. Like when I put x and y in the function, whatever z I get, I plot it, I will get this function. And this solid curve I have, it is having some height also. So it's in a 3D plane. And in exam also, you will get graphs like this, wherein you will be given some number, function will be given, some values will be given for A, B, C, D, and they will tell you, okay, for this scenario, what will be the volume? For this scenario, what will be the volume? That you have to calculate. So now let us try to find that. So now what we are interested in, let me write that. Now we are interested in yes.
Great. Sir, I just pressed some button by mistake. Did
No,
it?
that's fine.
Okay,
No,
okay.
no.
How do I stop? Okay, now it's I think it's gone. Yeah.
Okay, nice. So now we are interested in one very important thing, that volume of the solid. Under the graph of F. So we have a solid S. Volume of the solid S under the graph of F. and above R. So what it means is that, see, we have a solid S. So this is the solid S. Now this solid S is above a rectangle R. So this is the rectangle R. So we have to calculate the volume of that region. So what region we are interested in to calculate the volume? Let me shade it. This is the region we are interested. Like we get a solid object, 3D object. And we have to calculate its volume occupied by this 3D object. This 3D object consists of a solid S on top, whose nature we can get from the function itself, function with two variables. And it is above a rectangle R. So the height and all we can get from this rectangle R. And we have to calculate the volume of this shaded 3D object. And let us solve this problem using
Sir,
the concept of double integral. Yeah, please.
like say we found the height of the object, two-dimensional we have found, but the curve of the enclosing surface on top, that we won't be able to, even if we know the function,
Mhm.
unless we actually
Okay.
integrate the top, how will we know? I had this similar doubt earlier, I think. And you told me you only need two to find out the third. But now looking at the figure, I've got this doubt.
Yeah. No, very nice doubt. Very nice doubt. And now we can answer your doubt. See, what is happening is that if we know the function, that z is equals to, let us suppose, for example, x square plus y square plus 2. Then for every pair of x and y, I will get a z. Like when x is 1, y is 1, z will be 4. So I can plot it. So when x is 1, y is 1, z is 4. So I will get points. So the idea is that if you have this function now, like z is equal to f of x
Get
over
like a
y.
box kind of a box. You won't get like the depth and everything. Your depth is also there. Like the depth of the roof.
The depth though very easily we will get. We will show it.
Uh,
The challenge is this variable part. And this variable part will be given by the z is equal to f of x comma y, the function itself. Because whatever function we have, this is the domain. This region which I'm highlighting with a black pen, this region contains the possible values of x and y we can plug, and
Okay.
that is what we will take x and y from here, plug it in this, and I will get z. So I will get this figure, like the top I will get. And once I know the top, like the solid object, then so I simply have to draw vertical lines to get there and solve it. Now that is what we will see, how we will be solving it. Like how we will be getting the volume. Everything we will do step by step, so you will get a clarity what is happening. So let us do it step by step.
Yes, sir.
To get an answer. So first what we will be doing is that we will be dividing it into the interval A to B. See, this is the x-axis. This x-axis. This is the x-axis. And this is the y-axis. In the x-axis, we have A and B. Like in the x-axis, the graph is varying from A to B. So I can say that x can have any value from A to B. And similarly, y can have any value between C to D. Because for this rectangle, the x can be any A to B, between anything A to B, and y can be anything between C to D. Now what I will do, I will divide the x in the interval of the x into m parts of equal width. So the width of each part will be delta x will be b minus a by n. Like whatever is the interval, this interval, I am breaking it into m equally sized rectangles, and I am calling it delta x. Like equal width. I am breaking this region into equal widths delta x,
Hmm.
and I am breaking it into m pieces. So b minus a by n,
So just the x-axis.
just the x-axis. Similarly, just the y-axis, I will be breaking it into delta y is equals to b minus c by n. I will be breaking it to n pieces. So for the y-axis, I have small delta y's. And for x-axis, I have small delta x. Till here, it is clear.
Yes, sir, it's clear.
So I will bring in one more diagram to give you more clarity.
Oh,
Like
sir,
this,
how many they got a lot of diagrams.
yeah.
Uh,
Because that will give you a good understanding of it.
I mean, so let's just get to solving, sir. Come on.
Great.
So much there.
No, we are like.
Um,
So let us complete this. Because whatever base I am building now, with that only we will be able to solve graphical problems. Because they will be asking graphical problems. So whatever I have said, it is been done here. So see, this is the region R we are interested in, and this region R is this one, this same. This is the x-axis. This is the y-axis. Now see what we are doing. Now we have already seen that x-axis we are breaking it into delta x rectangles. M number of delta x rectangles. Can you see this? This is delta x, delta x, delta x.
Yes, sir.
And they are of equal width.
And then we randomly keep dots.
Yeah. And we have n rectangle delta y. Delta y, like this. Delta y, delta y. So we will get a grid like this. So in this grid, one of the side represents the delta x. Like this is delta x, then the other side will be delta y. So these grids are like small rectangles, wherein the length is like, let us suppose delta x. So the height or the width will be delta y. And what is the area of the rectangle? So the area of this small rectangle will be delta x into delta y. Are you are you okay with this?
Yeah, I'm getting it. So the base and then into height and then we like multiply it.
Yeah, yeah.
Yeah.
Because if I take any rectangle, let us suppose I'm taking this. So
Mm.
this line I'm drawing, this is delta x,
Mm.
and this height I'm drawing, it is delta y, because it is
Mm.
a y-axis. The
Mm.
area of this rectangle is delta x into delta y.
Mm.
Now, the idea is that this is representing a complete region. This is
Mm.
representing this region.
Mm.
In this region, I was able to calculate the area of a very small
Mm.
region segment or a sub-region.
Mm.
Okay. Now let us see more. Now let us take it further. Until here, the concept is clear. Now the idea is that in every rectangle, this black point which you are seeing,
Mm.
that is the point we plug. That is the point we plug in the fx comma y to get the height. Because see, what is the beauty of this representation is that width and breadth, like length and breadth is same for all, but height is the one which will vary. Do
Mm.
you agree with this? In this diagram, what I can say from this symmetry is that I'm talking about this diagram. I'm
Mm.
talking about this diagram. In this diagram, from symmetry, what we can say is that
Mm.
this this is a uniform region. Like equally sized rectangles will be there. So no variation. But what will vary will be the height. Because here you can see height is less. In the corners, you can see height is more.
Mm.
So and whatever is varying, we call it the function. So here the height is the function of x and y. Because for different values of x and y, the height is different.
Mm.
And this height I can calculate from fx comma y.
Yes, sir.
What is volume? Volume is height into area.
Mm.
Do you agree with this?
Yeah.
Can I say that small volume
Mm.
will be whatever area I have into f of xi comma yi, where
Mm.
xi and yi are the
Summation.
points of that rectangle, small rectangle,
Summation.
into no summation.
Like
See,
small points, like multiple similar small points.
no, we are taking only one. We are
Okay,
taking
okay.
this. So delta A is the area of this rectangle, and xi comma yi is the point.
Mm.
Xi comma y is the point, and if I plug it, I will get the height. So height into area is the volume. So small volume I will get. So let me bring in one more diagram visualization to get with more clarity. What is that? So this figure will give you more clarity about the scenario which we are discussing. Let me adjust. So see here, you can see that whatever we have discussed now, the same thing you can see in this visualization. I have a small rectangle whose area is delta A, and this point is xi comma yi, for example, this single point. So for this, I will get this height, or I will get this small region. That is what delta V will be. So delta V will be the volume of this small 3D object. Delta V will be the volume of this small 3D object. Now, one very interesting thing you will know is that now we have to do the summation as mentioned by you. To get the total volume, I have to add all the individual volumes, because here this delta V is the volume of one 3D rectangle, and we have so many. So what I have to do is that first I have to fix, let us suppose this one delta y I will fix, and for this delta y I have to iterate over n times. I have to iterate for delta x, delta x, delta x, delta x. I will keep on adding. So for a fixed delta y, delta x, I will keep on adding n times. So whatever 3D rectangles I am getting, its volume I am adding. Its volume I am adding. Then what I will do, I will go to the next delta y. And once again, I will be adding the 3D volumes. So here, double summation I have to use. Why double summation? Because inner summation will take care of this kind of a traversal, and the external summation will take care of this kind of a traversal, wherein for every row, I will be doing inner traversals to visit each 3D rectangle to calculate its volume and sum it up. Then I will be going to the next row and getting all the 3D rectangles and summing it up. Then to the next row. And this I have to do. And for the total number of rows, which is n. And hence, double integration I have to get the final one. So let us visualize that. Well, first, let us write it, then we will visualize it. So it is evident from whatever discussion we did until now, we can say that this V is summation of J is equals to 1 to N. I is equal to 1 to N. Isn't it? And I will do it for f of x ij comma yi. And I will, because dA will be same, like I will call it delta A. Because what I will do for different height, I will multiply whatever height I will get at that particular point. I will multiply it with the area to get the volume of that particular block. In this way, all the volumes I will get, I will add it up. And if I visualize this process, let us visualize whatever we have discussed. Now we are visualizing. Whatever we have discussed, we are visualizing.
Okay, like this. Oh, okay. Now I understood. The curve, it changes. You just change the height of the y-axis and automatically the curve will come because the rectangles are so small. Oh,
Yeah, so
oh,
this z, the value of height we are getting from the formula function. So we
so
are just, yeah,
uh, when does triple then see we've gotten the function also, then why do we use triple integrals? Everything is got here and we've got everything here, right?
double integral. Double integral we
I'm
are using,
asking
well, yeah, okay.
triple integrals is not required, right? Since you've gotten the what is the difference then, sir? Because with
Triple integral has a different purpose that we will discuss later on. Now we are discussing double integral.
yes, fine.
So here double integral, why we need it? Because double summation we have to do.
Okay.
We have to iterate in the y direction also and simultaneously in the x direction also, as we discussed.
Mm.
Right, just now we discussed the scenario wherein my requirement is that like I have to travel like all this one by one. So I will get the volume, I will add it, then this row, then this row. So
So I have to
double
do
integral.
like 2 minutes. Mm. I mean, you can just say I come and works.
Yeah. So let me adjust it. So now the idea is that in order to get the perfect volume, we have to do some approximation. The approximation says that we have to like see whatever we have it here, rectangles, they should be very small. The smaller these rectangles, the finer will be the calculated volume. So we have to make these rectangles extremely small. And how we will do that? We will do that by breaking the this AB region and CD region, that M and N, making it infinity. If we break this uh, region R into infinite number of pieces, then every rectangle will be so small and the volume will be finer and finer.
Mm.
So the approximation is that we are taking a limit wherein we are making both M and N tending towards infinity. With this approximation, the volume which we will get, it will be very close to the accurate volume. And this will convert into double integral. We can write it like this. Capital B is equals to double integral over the region R. Here R is a rectangular region. That is why the title of this session is this topic is double integral over the rectangle. So here capital R is the rectangle, that is the
Sure. Why do we take rectangle? Why not square? Why not So yeah, why not square?
Yeah,
We can take cubes, right? It look, but why rectangle?
yeah. No, no, cube to 3D, na? So it's a 2D plane, na? Cube to how we can take.
Oh, sorry, square. Sorry, sir. Square, square.
Yeah, yeah, yeah. We will look into it very soon.
Like this whole whatever figure is there, I can just draw one whole square, right? Like squares are much more
No, no.
proportional.
So see. The idea is that na, you can take square, you can take rectangle. Area is same.
Uh,
For square also, area I can take it side square.
uh,
What is
hmm.
the area of the square? Side square,
A into A, yeah.
A into A. So I can take it side square, or I can take it A into B.
Hmm. Hmm.
Rectangle we are taking to make it more generic. Because square is a specific case where there is a constraint that both the sides should be same, and we don't want that constraint. Na?
Okay. Okay, fine. Hmm.
We are making it more general because ultimately it is a technique. It is a mathematical technique to calculate the volume. It's a mathematical technique.
Hmm. Hmm. Hmm.
So in this technique, we are taking small like
Hmm.
dx and dy we are taking. Now
Hmm.
this dx and dy, it is not needed that they have to be same.
Hmm.
This dx and dy can be, they can vary also. Why they can vary? Because they are so small. How we can ensure that both will be same?
Hmm.
We can't ensure it, no? And hence rectangle is a better tool for us
Hmm.
because now we are not worried. If we are taking square, then every time we are worried that these two things has to be same. How we can ensure that? We cannot ensure. But if we are taking rectangle, we are not at all worried. They
Hmm.
can be. I know that dx has to be very small. It can be anything. And dy has to be very small. It can be anything. There is
Hmm.
no relationship between dx and dy, and hence
Hmm.
rectangle is a better choice,
Hmm.
isn't it?
Yes, sir.
Yeah. So now we will convert it. So we can write it, and what it will become? It will become dx. So this is the double integral. So now we got an idea that whenever I'm talking about double integral, I'm sweeping over a rectangle wherein I am breaking the rectangle into very small rectangle, and I am plugging the value of x comma y of that rectangle into the function to get the height. So
Hmm.
I will get a very small volume of a very small rectangle, like 3D object. A
Hmm.
very
Hmm.
small volume I got. I will keep on adding those volumes,
Hmm.
keep on adding, and ultimately I will get the volume,
Hmm. Hmm.
total volume of the object. So this is a mathematical technique, and it works so fine
Hmm.
because we are convinced that yeah, it will work. Because whatever we have discussed, it's logical. It is completely making sense.
Hmm. So now we'll get to questions, sir.
But one question we will do. One question we will do. Just a
Fine.
minute. Yeah, we will do one question. We will do one question. So here, this sum which we have done, that we call it like double Riemann sum.
Uh,
I will know. Double Riemann sum. Now let us do one question. in the exam, you can expect a graph like this. So we are solving a graphical question. Or if graph is not given, this function will be given. This function will be given, and x and y will be given, the interval of x. That also I will present here. So both the way I will present the question which you might get. Either you will be given a graph or you will be given some statement that I will write. And how to solve this, that will be discussed. So the idea is that here we have been given a graph, or you can make write. You might be given a statement also. Let me write that. Find.
So, but then without the graph also I can directly integrate it. Huh?
Yeah, that is what. That is what. So both the way I'm telling.
Yeah.
Either you will be given a graph, then to easy to visualize, and
But
here
the function anyways they have to give, right?
no, that in the graph they have given. No? So that is what I'm telling.
So, okay, okay.
Either
Yeah.
they will give the graph. If they are giving the graph, in the graph itself, they will give all the information. Function is given, and this x and
X-axis,
y,
yeah.
x axis and the range is given, like 0 to 2. X is from 0 to 2, y is also from 0 to 2. And or they will not give the graph, they will give the statement. That is what I'm writing. So they will say that find volume of the solid. And then they will give some parameters like the function and all that I'm writing. So here f of x, or they can do f of x comma y. Like they can do like z is equals to f of x comma y is equal to 16 minus x square minus 2y. And they can give the interval of x and y. So they can say that x lies between 0 to 2 and y also lies between 0 to 2. This is the now we have to solve. So we can straight away solve it, but like we will first feel it. Whatever we have discussed, we will feel it in that way, then we will solve it. Then it will be very good for you. So see, the idea is very clear. The idea is clear in such a way that, and it is also given in the question that uh, divide R into 4 equal squares. It is also given. I'm writing it. So, isn't it? So if I plot the graph, the R region, So see, the idea is very clear. This will be x. Let us suppose this is x, this is y. Now this is origin. Now here x will be from 0 to 2. So this is 2. And y is also from 0 to 2. So this will be 1, this will be 2. So delta A, here it will be 1. Because 1 into 1, small area will be. Now I know how to calculate the volume. To calculate the volume, what I will do is to calculate the volume, what I will be doing is that f of, I will write it for f of xi comma yi into dA. What is dA? dA is dx into dy. Small dx, small dy. And double summation. And instead of d, I will take delta A. I will take delta A. And I will be doing double summation. And let us, I'm taking it like j is equals to 1 to 2. I is equal to. And this will be the volume approximately. The volume will be. Now what I have to do is that 4 rectangles I have to get the height of this. So for height, I can take the corners. Like 1 comma 1 can be 1.10, 2 comma 1, then 1 comma 2, 2 comma. So let me do that. F of 1 comma 1 into delta A. Delta A will be same for all. Delta A is 1. Like now I am writing for formula, but I know its value. 2 comma. Then 1 comma 2. Then 2 comma. So now we will be solving it. In this function, f of 1 comma 1, if I put, what I will do? So 1 minus 2 minus 3. So 16 minus 3 is 13.
Okay.
So 13 into 1 plus 2 to the 4, 4 minus 2, or like minus 4 minus 6, 10. plus 1 comma 2, 4, 4 to 8, 9, 16 minus 9. Okay, it will be 7. 2 to the 4, 4 to the 8. 9, 7, 8. 1 comma 2, 4 to the 8, 9. 2 to the 4. Yeah, it will be 10. The last 2 comma 2. So 4 minus 12. So 4. After all the solving, you will get the answer. That is 34. So this is one method. Now the easy method I will discuss. Like, okay, this is for understanding, but straight away, one direct method we can adopt. And the direct method says that, okay, this is the integration we have to do. So let us use the concept of double integral. F of x comma y dx dy. So fx is 16 minus x square minus 2y. Straight away do dx dy. Now, if you are doing dx first, whatever order you can do, it is fine. But you have to be careful that if you are doing dx first, then here you have to take the y is equal to integrals of y.
Okay.
And here you have to take the integrals of x.
Mm.
Here both are same, so it will not make any difference, but it's very important that consideration.
Sir, if I'm doing a dx first, then the first integration would be x lim or y limits.
Yeah,
For x,
please. Yeah, please be very careful. You are right. See, whenever you are doing first, you are integrating with respect to x, limits will be y.
Okay.
Yeah, only this thing you should be aware of. Then, so it's very easy. Then straight away we can integrate it. And when you will integrate it, if you are integrating it with respect to x, y will be treated as constant. So 16 minus, okay, so we can do that. Let us try this. So this will be integration from 0 to 2, like the outside. In the inside, you will get what is the integration of 16? 16x
X
minus
x to the power 3 by
minus 2y square. Because 2y square will be treated as constant. And the limits we have seen it is 0 to 2 dy. Now we can
substitute out. So should I substitute the limit or didn't
yeah, you have to first you have to substitute the limit. You have to get rid of x.
Okay.
Let us get rid of x. We have to get rid of x for peace.
Okay.
Yeah. So that there will be no mess. So let us do it. Now, when I put the limits, so 16 into 2, right? Okay, let us calculate. Let us not be lazy. So 16 to the 32 minus 2 to the 4, 45 minus 4y minus. Okay, here everything will be 0. So 32 minus 8/3 we can do. So let it be like this, and let us solve it once again. So it will. So now we are integrating it with respect to y. It will become 32y minus 8/3y minus 4y cube by, and it will be from 0 to what it will be. 64.
Mm.
16 by 32 by 2. Please solve this. Let me make this calculation. Okay. So see, we are getting 48.
Mm.
You see the difference. So with the normal method, like we are not breaking it into infinitesimally small,
Mm.
we are getting 34 as the volume. But with the appropriate approximation, we are getting 48.
Mm.
So this is the right answer. So this approximation plays a very important role, and this I will demonstrate with the one more figure. This figure makes sense.
Mm.
Let me make it small. If you look at it, you can see that as we keep on increasing the size of m and n, like as we are breaking the rectangles into smaller and smaller pieces,
Mm.
the volume we are getting it is increasing.
Mm.
Here we have 4, like m and n is 4. So it means that uh, 4 rectangles we have along an axis. 1, 2, 3, 4. 1, 2, 3, 4. Here we have 8. 1, 2, 3, 4, 7, 8. Here also 1, 2, 3, 4, 5, 6. So what we can see, volume is increasing. And here the volume is increasing more because 16 rectangles we are having. Like we have broken the x and y into 16 parts, and we can break it into infinity parts. We can break it into infinite parts. And that is what, and when we do that, we will get 48 as the answer. That's the right answer. So see how magical it is.
Yes, sir.
Like with this mathematical technique of integration, double integration, we are able to estimate the
Accurate.
volume
Yeah.
accurately volume of a curve. And the interesting thing is that this curve is so, like, it's not symmetric now, because this its height is varying so weirdly,
Mhm.
as we saw. Now that that height is being taken care of by the function itself. So this is a very interesting technique, a magical technique to calculate the volume of a curve.